Okay, now we see the modulators of ssb-sc, which is frequency discrimination method and phase discrimination method. Okay, now we go for demodulators of ssb-sc. Then obviously there is no other option. All suppressed carrier modulation techniques, all suppressed carrier signal will be demodulated only with the help of one demodulator. That demodulator is nothing but synchronous detector. Now just see the transmitter portion first. Synchronization, right? Now this is m of t, product modulator or balanced modulator AC cos 2 pi fct plus this is dsb-sc signal, but I want an ssb-sc signal. So using a proper filter, you can get back an ssb-sc signal. Okay, for comparison. Okay, otherwise you go for phase discrimination method also, not a problem. Now this is ssb-sc modulated signal, and this is the transmitter portion, right? This is the transmitter portion. But our demodulator, this is a part of receiver. Okay, I am concentrated on receiver part. So this is the transmitter portion. Now this is the transmitted signal is ssb-sc signal. Now this is the received signal is an ssb-sc signal is the received signal. Okay, so this ssb-sc signal is the received signal. Now this is product modulator at the receiver side, and another input to this product modulator is local oscillator. Okay, now this local oscillator will generate the carrier whose frequency and phase should be matched and should be used at the transmitter side. Okay, so my local oscillator is able to generate with the same frequency, same phase is good. Otherwise we are facing some problem, but I am saying that there is a phase mismatch of, there is a phase difference of phi between the carrier used at the transmitter and a carrier generated at the receiver by using local oscillator. There is a phase mismatch. What happened, the phase mismatch? We already covered in AM and DSB-sc, but now we will see in ssb-sc also. So what is the output? Okay, now what is the output of the product modulator at the receiver is the output of product modulator at the receiver is ssb-sc signal multiplied with local oscillator generated signal. ssb-sc signal is AC by 2 m of t into cos 2 pi fct minus or plus AC by 2 m cap of t into sin 2 pi fct multiplied with local oscillator generated signal is AC cos 2 pi fct plus phi. So then this is multiplied, and finally we want a low frequency information signal. This is passed through a low pass filter. So what is the output of the demodulator? Now if you simplify this, now the output of the synchronous detector is AC square by 4 m of t into cos phi minus or plus AC square by 4 m cap of t into sin phi. Okay, you just multiply this one, expand this one, cos A cos B minus sin A sin B, and you multiply these two terms with those two terms. So somewhere you can have this one also, cos square theta, you can be 1 plus cos 2 theta by 2, you can write it, or sin square theta, or also you can write 1 minus cos 2 theta by 2. So if you replace these two formulas in this expansion, and you can get the answer is this. After passing through the low pass filter, this is the output. This is the output of the low pass filter, or output of the demodulator. Now this is the transmitter portion, and this is the receiver section. This is the transmitter portion, and this is the receiver section. Now you see here, now there is a phase mismatch. Suppose if the phase difference is 0 degrees or 0 radians, means at the transmitter side phase is 0, receiver side phase is also 0. If phase is 0 degrees or 0 radians, then the output of the detector is AC square by 4 m of t into phi is 0, cos 0 is 1. Next, if phi is 90 degrees, if phi which is equal to 90 degrees, so output of the detector is AC square by 4 m cap of t into sin 90 is 1. Both are perfectly synchronized. M of t is also having a message signal of amplitude AM. M cap of t is also having a message signal of amplitude AM. Only phase is different. Not a problem. Okay. Now, which means that now perfectly synchronized. What is the problem we just observed in the synchronous detector when we are used this in AM and when we are used in ssb-sc? The same synchronous detector which we are already used in AM, already used in ssb-sc demodulator, AM demodulator. There we are facing one common and continuous problem arises, that is nothing but when phase is matching perfectly synchronized. But when phase is mismatching at a phase of 90 degrees and output equal to 0, then that effect we call it as a quadrature null effect. But what about the quadrature null effect in the case of ssb-sc? So when phase is 90 degrees, output is a message signal. Okay. So there is no quadrature null effect. There is no quadrature null effect. There is no quadrature. There is no quadrature null effect in the case of ssb-sc. This is another great achievement or advantages of ssb-sc. Okay. Now this is of course cost, complexity, synchronization is a difficult task, but there is no other option because all carrier suppress techniques are demodulated only with the synchronous detector. But one advantage we gain here, there is no quadrature null effect in the case of ssb-sc, but AM demodulator suffers with quadrature null effect. ssb-sc demodulator is also suffered with quadrature null effect, but ssb-sc demodulator does not affected the quadrature null effect. So there is no quadrature null effect in the case of ssb-sc. Even you are using a same synchronous detector which we are already used in AM and dsb-sc. The reason behind here, the ssb-sc is generated based on the phase discrimination method. So because of this phase, so there is no output is not equal to 0 and there is no quadrature null effect. Okay, note down. Okay. Now you know the modulator, demodulator, and what is the ssb-sc modulation technique. Then we will start with advantages, disadvantages, applications. Okay. So this is the end of any modulation technique what we are doing the procedure. Now first we will see the advantages. Tell me now, what are the advantages? N number of advantages you observed. The main advantage, okay, very important advantage. the bandwidth of ssb-sc, the bandwidth of ssb-sc, which is equal to omega hertz, which is less compare with, which is less and reduced by 50%, which is less and reduced by 50% when compared with bandwidth of AM or DSB-sc. Bandwidth which is equal to omega hertz, which is less and reduced by 50% when compared with bandwidth of AM or DSB-sc. Now see here, this main bandwidth which is very less and which is 50% reduced compared with AM and DSB-sc, that will give a very good advantage for us. Now see here, which of the following modulation technique is less affected by noise, is one question I just write here. Which of the following modulation technique is less affected by noise? I am giving the options also: AM, DSB-sc, ssb-sc. Now, which of the following modulation technique is less affected by noise among these three? If you take among these three, now without any second thought, now see here, one small story I am explaining here. The noise power which is directly proportional to bandwidth. Okay, so the noise power is directly proportional to bandwidth because the noise power which is equal to K Tn into B, Boltzmann constant, noise temperature, bandwidth. Okay, K is Boltzmann constant, Tn is noise temperature, B is bandwidth. Therefore, this is K is constant, noise temperature is constant, so the noise power is directly proportional to bandwidth. So as bandwidth is increases, then this noise power is increases. As bandwidth is decreases, this noise power is decreases. Now see here, as bandwidth is increases, noise power is increases. As noise power is increases, what happens? Signal to noise ratio is decreases. When signal to noise ratio is decreases, which means effect of noise is more. Effect of noise is more. Clear or not? Now you tell me here, now the bandwidth of AM is 2 omega, which is very high. The bandwidth of DSB-sc is 2 omega, which is very high. But bandwidth of ssb-sc is just omega. When bandwidth is less, noise power is less. When noise power is less, signal to noise ratio is more. Now where the effect of noise is less. Therefore, ssb-sc, which is less affected by noise when compared with bandwidth, when compared with AM and DSB-sc technique. Now I am giving the same question, but another options I am giving. Now which is AM, which is DSB-sc, which is ssb-sc. Now which is FM, frequency modulation. Okay. Now see here, all these are derivatives of AM. All these are AM, amplitude modulation technique. Okay, AM techniques. All these are the AM techniques. What is AM? Amplitude modulation. In amplitude modulation, the information is in terms of amplitude. AM means information in terms of. AM means information in terms of amplitudes. When the noise is coming and it is first affected the strength is nothing but amplitude. So when the information itself in terms of amplitude, effect of noise is more. Effect of noise is more. But this is the frequency modulation. The frequency of the carrier is changed in accordance with the amplitude of the message signal. Even if the noise is coming and affected the amplitude, information is not in terms of amplitude, information is in terms of frequency. Okay, so here information is not in terms of amplitude. This is FM modulation, frequency modulation, which is the least affected by noise in all the analog modulation techniques. So with respect to noise, the best modulation technique is nothing but FM. Okay, very soon we will see the FM modulation technique. Okay, so when these four options are coming, so here information is in terms of amplitudes, therefore effect of noise is more. Here information is not in terms of amplitude, in terms of frequency. This is frequency modulation, but noise is coming, amplitude is affected. Even if amplitude affected, not a problem. Here information is not in terms of amplitude, information is in terms of frequency. But noise is coming, first affected the amplitude, already information is available in terms of amplitude. Information is affected, amplitude affected. But here amplitude is affected, information is not affected, because information is available in terms of frequencies, because this is frequency modulation. Okay, so FM is least affected by noise. Okay, but is there any digital systems comes into picture? Obviously the digital system will be the best one with respect to noise. Okay, so in analog, FM is best. So the same question like this, another options: A, AM, B, ssb-sc, C, FM. Now D, pulse code modulation, PCM, pulse code modulation. Okay, all these are analog. So analog means continuous wave signals. Now we are more affected by noise, and it is somewhat difficult to retrieve back that particular original signal from the noise. But this is a digital pulse code modulation. This is the digital signals. Now digital signals is nothing but binary ones and zeros. The information is in terms of ones and zeros. Where the noise is affected affected by the ones and zeros, you can easily get back the ones and zeros, because eliminate the noise completely. So the least affected by noise among these four group is nothing but PCM. Okay, so this is okay. Anyway, this is important. Okay, now ssb-sc is least affected by noise when compared with AM, because bandwidth is more here, bandwidth is less. Okay, no doubt. Single sideband suppressed carrier modulation technique is less affected by noise. Now the third one is single sideband suppressed carrier modulation technique is less affected by noise, and power saving is more in ssb-sc, and power efficiency is 100%. Power efficiency is 100%. And another important one, there is no quadrature null effect. There is no quadrature null effect in ssb-sc. Okay, so these are the main advantages of ssb-sc. Now single sideband suppressed carrier modulation are less affected by noise with respect to bandwidth, and these are the main advantages. Am I not? So what about the disadvantages? Tell me, What about the disadvantages? Disadvantages is, now the disadvantages of ssb-sc is ssb-sc generation methods. What about the generation methods? There are two methods here, right? One is frequency discrimination method or filter method. Now there is some problem with this filter method. The filter method I am already explaining. Practical filters not having sharp cutoff frequencies. Ideal filters are not available practically. Okay. Now this is the filter method problem. Now in phase discrimination method, the problem is hardware complexity is very high compare with filter method. And another advantage is hardware complexity is very high compared with filter method, and valid for single tone. Not valid for multi-tone. Maintain 90 degrees phase for all frequencies. Or difficult. These are the problems what we are faced in filter method as well as a phase discrimination method. So the disadvantage itself is a demodulator. The disadvantage itself is a generation of ssb-sc. The generation of ssb-sc is there is a two methods, filter method, phase method. Now these are the problems we are facing. Not only that, and of course the demodulator of ssb-sc is nothing but synchronous detector. Synchronization itself is a very difficult task. Cost complexity increases, and of course one advantage we are gaining in the detector method, synchronous detector method also, there is no quadrature null effect. Okay, these are the advantages and disadvantages. Now we will see the important one, which is nothing but application of ssb-sc. Okay, before that you note on this. Applications. Okay, so this ssb-sc is used exclusively for the transmission of ssb-sc is used exclusively for the transmission of voice signal. So here two words you underline, voice signal and ssb-sc. Okay, there are a number of modulation techniques, AM, DSB, SC, SSB, but this is exclusively, especially best suitable for transmission of voice signal, he is mentioned. Now what is the reason behind that? Now you just see, observe here. I just given the frequency domain. Now this is voice signal. You know the frequency range of voice signal is 300 Hz to 3.5 kilohertz. Now this is the okay, and this is the spectral gap. This is spectral gap. What is the spectral gap? 300 and 300. Now this is the spectral gap, 600 Hz between the upper sideband and lower sideband. You just observe this one. Now there is a spectral gap of 600 between the, now if this is a voice signal, okay, now see here, this is a voice signal. Now the spectral gap now between the two voice signal, which is 600 Hz, okay, when it is going for modulation, means modulate with the help of carrier. So this origin is shifted to FC. Now this is FC plus 300. This is FC plus 3 point, means after modulation. Now this is FC minus 300. This is FC minus 3.5 kilo. Again spectral gap. Now this is modulated signal. Okay. Now see here, there is a spectral gap of 600 Hz, but to modulate this signal, and voice signal is transmitting some modulation technique. Let us assume some modulation technique. But now let us assume I want to take a demodulator. I want to take an ssb-sc signal. So ssb-sc generation is nothing but there are two methods, filter method and phase method. Therefore I want to take a filter method. So what is a filter method? The filter method means ideal filters are not available. Practical filters. Take a practical filters. Now see here. This is the practical band pass filter I am taking here. This is the practical band pass filter. Now see here, this is FC plus 300 to FC plus. This is the practical band pass filter. Now this is having a transition band. This is the pass band. This is the pass band, and this is the practical band pass filter. Now see here what happened. Now the practical band pass filter will not have a sharp cutoff frequencies. It is having some transition bands. Not a problem. Even if the transition bands are available. Now where is this transition band? This transition band is available in the spectral gap. No problem. Nothing is there in the spectral gap. So because of the large spectral gap, so the voice signal is successfully transmitted by using an ssb-sc modulation technique because of the large spectral gap. By using which filters? Practical filter, practical band pass filter. This is the practical band pass filter. The practical, what is the meaning of that? The practical band pass filter is here. The practical filter is not having sharp cutoff frequencies. We know that, but that sharp cutoff frequency is not available. Not possible to separate one sideband completely. But now with the practical filters, I can separate. This is upper sideband and this is lower sideband after modulation. So by using practical filters, can I separate one sideband completely? Yes, you can have one sideband completely. So with the practical filters, I can separate one sideband completely. So you tell me what is the advantage. So ssb-sc is the best suitable for transmission of voice signal because of, tell me, because of large spectral gap, because of a large spectral gap between the voice signal. This is a large spectral gap because voice signal because of large spectral gap of 600 hertz. Okay, note down. Between USB and LSB. This is the first point. So what is the second point? The second point is the practical filter can easily separate one sideband completely even the filter does not have sharp cutoff frequencies. Clear or not? So this is the another advantages of choosing ssb-sc for transmission of voice signal. So we can accommodate more number of voice signals within a channel bandwidth. So if your modulator is ssb-sc rather than AM and DSB-sc. Okay. And now see here. Now this is the spectrum of audio signal. Okay. Small concept. This is 20 hertz to 20 kilohertz. Now this is between upper sideband and lower sideband. Now what is this spectral gap? Here, if you observe here, the spectral gap of audio signal is 40 Hz. Spectral gap of audio. Spectral gap of audio signal is 40 Hz. What is the spectral gap of video signal? This is the video signal. 4.5 megahertz. So the spectral gap, which is how much is the spectral gap for video signal? See here. Now spectral gap of 0 Hz for video signal. I hope you understand what is the importance of spectral gap after completion of ssb-sc. Okay. So when the spectral gap is very less, here gap is 0. When the spectral gap is very less, it is difficult for the practical filter designing point of view, because the practical filters are not having a sharp knife. The practical filters are having a transition knife. Am I not? So it will not cut at the same point where you want to cut. So it will cut somewhere. So that somewhere the information will not exist. The information will not exist means there should be a large spectral gap. So it is possible to separate with the by using a practical filters. Okay. So this is the spectral gap of audio signal is 40 Hz, video signal is 0 Hz, and you already know that our voice signal is 600 Hz. Okay. So how you can trace out the video signal? Okay. How to transmit a video signal? So first of all, so this video signal, if you transmit, okay, for transmission of video signal. So this video signal transmission is possible with AM or DSB-sc. What are the problems we are facing? You just concentrate here. Transmission of video signal. Okay. transmission of video signal. Let us say here, this is the transmission of video signal. Now, if you want to transmit this video signal by using AM or DSB-sc, not a problem, okay? AM or DSB-sc, what happens? If you want to transmit this video signal by using amplitude modulation or DSB-sc modulation, what is the bandwidth required? The bandwidth required to transmit is 2 omega, where omega is 4.5 mega, which is equal to 9 megahertz. The bandwidth required to transmit an AM or DSB-sc signal is 2 omega, which is equal to 2 into 4.5 mega, which is equal to 9 megahertz, which is too large for multiplexing point of view, which is too large for multiplexing point of view, because to transmit more number of signal, what is the condition? The bandwidth of the modulated signal should be as minimum as possible for multiplexing point of view. Right? So, if I use an ssb-sc, now the bandwidth required is omega, which is equal to 4.5 megahertz, which is good, which is less, but it is best suitable for voice transmission. So this is too much and this is good. This is very high, this is less, but this is not at all useful, but this is used by some other person. Okay. So now you have a compromise. So we have to compromise. We required a new modulation technique whose bandwidth we required a new modulation technique. We required a new modulation technique whose bandwidth, which is far less than 2 omega, just greater than omega. Okay, we want that. We require a bandwidth of a new modulation technique whose bandwidth is far less than AM and DSB-sc bandwidth, whose bandwidth is just greater than, because exactly equal to is not possible by using the practical filters. Okay, so how can we get this new modulation technique? How can we separate one video signal separately? Okay, there is no other option. The practical filters will not have a shortcut of frequencies. The practical filters will not have a shortcut of frequencies. Now concentrate here. Now after modulation, this is FC plus 4.5 megahertz, right? FC minus 4.5 megahertz. Now let us take, this is upper side band, this is lower side band, video signal after modulation. Right? Now I want to take one sideband completely, but not possible by using practical filter. It is possible by using an ideal filter. If you take an ideal filter, this is exactly cutted here. Okay, but no ideal filters are available. You have to take care. You have to design only a practical filters, so such that you design a practical filter like this. You design a practical filter like this. Now see here, this is FC, this is FC plus omega. So you design a practical filter. Now this is the practical filter, is having some transition band. One side there is no problem, Now the another side, should be as minimum as possible. The another side should be as minimum as possible. So now see here, this is the practical band pass filter. If you design like this, this is the practical band pass filter. This is the practical band pass filter. Now this is Fc to Fc plus omega. This is Fc minus Fp. This is the practical band pass filter. So now you see here, this is the pass band. Then there is no other option for the other side. Okay. Now if you design a filter with this small transition from other side, because there is no need, there is no way to cut exactly at Fc, right? So this is one sideband, completely we can get it. One sideband, single sideband, and a small portion from other sideband is also coming. We cannot eliminate that, a small portion, because there is a 4.5 megahertz from the other side. It should be minimized as less as possible for designing. That depends upon the designing of the filter. So if you design this filter with an appropriate care, this is Fc and this is Fc minus Fp. This is single sideband and this is a small portion. A small portion. See here, one sideband and a small portion or a small width. This small portion or a small width is called as vestige. Plus this is single sideband. Now this new modulation technique, which is named as finally VSB, vestigial sideband modulation technique. Vestigial sideband modulation technique. Don't confuse, no vestigial sideband, nothing. This is nothing but an ssb-sc modulation technique itself. Single sideband suppressed carrier modulation technique. Only the thing is designing of the filter. Take care of an appropriate way to design the characteristics of filter in such a way that this side should be very, very small. Now in a remaining all cases, the pass band, the gain is constant in throughout the pass band. Am I not? The gain is constant throughout the pass band. Like this we are designing a filters. Okay. But here, so you design a practical band pass filters. So throughout the pass band, the gain is not constant. It is gradually decreasing in such a way that so the other side information should be as minimized as possible, and compare with the original information, this should be negligible one. Okay, not a problem. So you cannot suppress this one completely because the practical filters will not have a sharp cutoff frequencies. Okay, so this is the vestigial sideband. Now what is the bandwidth of vestige? So what is the bandwidth? This is the bandwidth. What is the bandwidth? Omega plus FV Hz. This is the bandwidth of vestigial sideband modulation technique. This is the bandwidth of vestigial sideband. The bandwidth of VSB. This is the best suitable for transmission of video signal. omega plus Fv. And this portion, okay, which portion? The width of the vestige. Width of the vestige is, the width of the vestige is from Fc minus Fv to Fc. The width of the vestige should be as minimum. The width of the vestige should be as minimum as possible. As minimum as possible. The width of the vestige should be as minimum as possible. Width of vestige. Width of the vestige is decreased. Width of the vestige is decreased by higher order filters. Width of the vestige is decreased by increasing the order of the filter. By increasing the order of the filter. If you go for a higher orders, then your width of the vestige should be as minimum as possible, such that you can get the minimum bandwidth. Okay. Now this is the vestigial sideband modulation technique, is the best one to transmit a video signal. And the modulation and demodulation techniques of modulation and demodulation techniques of VSB should be same as that of ssb-sc, except filter characteristics. That's what we will just put the name, otherwise everything will be same. So design a practical filters, and I am already explaining, in remaining all cases throughout the passband gain of the filter is constant, but in this case over a passband the gain is not constant, the gain is gradually decreased over a passband such that it will cover a small portion the other side. Okay, no, very important.